Okay, so yeah, as I think
there's 10 minutes at the end for summary.
Yeah.
It's got 10 minutes.
Yeah. Okay, so we do have a couple of presenters who present results. So myself and Ashton are going to show. I think we're putting our hands up to say we are not the expert companies out here. So if you think all the results look bad, don't assume that that is the current state of the art for all of AI/ML. But hopefully it's some learnings. So as I kind of alluded to, there are lots of applications of machine learning to CFD. I'm a big fan, though, of saying, whilst ML could be used, is there a net benefit? It's sort of the classic argument of, yes, you could run a massive simulation, but if it costs you $1 million to do the simulation, you may as well just do it in the wind tunnel. I mean, the cost saving, it's so expensive to do it, it's not worth it. So I think it's interesting to look at the, and that wasn't a jibe at anybody in particular, the runtime accuracy. People online won't know what I'm talking about, so it's fine. So whenever a particular method is proposed, I think it is also worth considering the runtime, the accuracy, and the cost. So even for an ML approach, how long it takes to run, how accurate it is, and what's the cost are useful metrics. And it's only truly fair if you include how much trained data was required, and the time and cost to create the trained data, the time and the cost to train the model, the time and the cost to do the inference, and the accuracy. If you only pick one of those, it's sort of not a true comparison against it. Now, the problem, at least from what we can see, is that there are so many different methods emerging that it is not just one. This is sort of more of a flow chart, I guess, of different approaches. But if we're focusing more on surrogate models, the big debates are between these data-driven, and just a brief summary, data-driven means I don't tell it anything about the physics. I don't enforce boundary conditions. I don't tell it anything about that it should conform to a energy conservation or mass conservation. I just assume that given enough data, it will learn those relationships. Or physics-driven, where I try to impose a particular constraint on, let's say, a boundary condition, or I impose some of the equations indirectly. But like anything, you could do a bit of both. And so there are many, many different approaches out there. So when someone says machine learning the CFD, the question should be, well, which approach? And this is where the nuance comes in. And I think it's probably fair to say that this is such a emerging area where it's not clear what is the best approach, and it's not clear in 1 year's time will that change, or in 2 years or 3 years' time. But I think it's fair to say that there was a seminal piece of work by Google DeepMind in the MeshGraphNet paper that really sort of kick-started a lot of this work. Because previously a lot of methods assumed that you needed a structured mesh as an input to these methods, or you would take some images, let's say. Whereas we know in CFD, many people have meshes, unstructured meshes quite often, actually. And so the MeshGraphNet basically showed how you could take a mesh and use graph neural networks, which are very, very popular, actually, for social media companies, for intelligence agencies, and all these other places, and try and use that to solve science problems. And probably the most well-known of that now is GraphCast and many of the weather prediction models that in some ways are simpler because the Earth is always the Earth, so you don't have many geometry changes, but still it's showing the potential of what it is. And so they showed as well that from MeshGraphNet you could apply this to CFD problems. And so that's one of the things that we're going to show. But the problem is that, at least in the public literature, there are no examples, that I've seen anyway, maybe something's come out recently, where somebody has shown using these for 300 million cells. Yes, there are many examples for simpler problems, but the scale is challenging. So one thought that we had, and others have had as well in the literature, is it really necessary to try and predict the full flow field? If machine learning is about a fast tool to look at conceptual design, what about if you try and be a bit more pragmatic and predict some things directly? So what we're basically showing in this presentation is the application of some methods to the DrivAer mainly, and a little bit to the Windsor, for a MeshGraphNet variant, but that actually tries to do something a little bit different, which is trying to predict directly some quantities. Okay, and we actually have a paper on this. I can send a link that probably is worth reading if you want to know more. So the first method is what we're calling direct KPI. So you take the mesh, the STL of the mesh, using MeshGraphNet, and you link that directly to the drag, to the lift, to the side force. So there's no flow field, there is no physics. It is a data-driven model linking the geometry to the forces. And so in this example, we take the entire data set. That means we take a 60-20-20 split. So about 290 cases are for training, 97 are for the validation of the model, and then 97 are completely unseen by the model and only tested at prediction time. And there's probably a lot to read on this, but essentially that graph on the left is the actual versus predicted. Some people are very familiar with these graphs. And what we see is that there is about a 1.4% error, about, I think, 0.0039. Does that count? Is that 4 counts? I can't remember how you do the 0.004 4 counts. Yeah. And what, interestingly, we came up with a metric, directional correctness. So basically, we look at all the data set, run 1, run 3, run 5. Is run 2 bigger than run 1? Is run 4 bigger? And we calculate with the predictions, do they at least get the right direction between it? And for this, there's about 91% accuracy. I honestly don't know what that would be for a normal CFD approach, but that seemed sort of reasonable. The main thing, though, that I thought would be interesting to show is that roughly the training cost is about $60. It's about 2 hours to train on a L40S, whereas the inference time is 1.2 seconds. And so, Herbert, you can put that in your table, because that's 80,000 times faster. Now, I'm sort of joking a little bit with a wink there. It's technically true, right? The inference is 80,000 times faster, but it's not. I mean, let's be honest. I'm predicting just a direct drag, and your CFD solver's giving me an entire flow field and everything. So it's not a fair comparison. So it's a bit of a tongue in cheek, but it is true that it is very fast to do the inference. But remember, this method is just taking the STL. So it is nice because it's not a parametric model, it's a non-parametric model because I'm just taking the geometry, and I'm only getting the drag on the lift. But if you do this now for the lift, you get a sort of similar sort of accuracy error for this, and then this is just the loss plots if you want to see. We've got like the CLF, now the loss plot, and then CLR. So they're not all sort of perfect, but then what I did is I took the baseline driver is not in the data set. So we have run now the baseline driver, and so I did a prediction basically. I took that model and did it, and you can see for this it actually does a pretty good job. So the CFD, because remember there is no experiment because we're really testing into the CFD. So it's pretty close actually. 3 counts difference and all the rest of it. But I promise you, there are plenty of results I've seen which are way worse than this. So this is not, I think the data set feels to me a little bit easier to predict on. You'll see later in Windsor, we have a much harder time. The second one is 2D image slices. So we thought, what if we could actually predict the images? So now we're using an autoencoder approach, which is quite popular in computer vision, with MeshGraphNet. And so what you see on this, so the left is the CFD and the right is the ML prediction. You can see this sort of blurriness. It's quite common actually with autoencoders. This is still, basic preliminary work. I'm sure somebody could do this better. But it is kind of interesting how you can train a model, because at least our observation is that many automotive companies have pictures. your standard post-processing is spit out 400, it certainly is in Formula 1, spit out like 400 images in X, 200 in Y and Z, and you just flick like a picture book. So we said, well, why can't we just take those? So the model is literally just taking in the PNG images, and that's one test geometry, that's a second, that's a third, that's a fourth. So there's still, like you can see here, it's absolutely not perfect, but just conceptually, I think it's kind of interesting. I should say though, I think I skipped over at the beginning, this definitely takes longer to train. And so this actually took us about 27 hours to train, so it's about $400. So there's a lot of images. I'm sure you can make this more efficient, but the inference is still the same, 1.2. Okay, that was the slices. Now, the 3D surface mesh. This is probably the most intuitive thing that people want to be able to predict because you can visually see the pressure, the wall shear stress, and you can calculate from it. Burkhardt told me he hates it when people just put a picture in and he say, oh, it kind of looks the same. It kind of looks the same, doesn't it? So, so it's a little bit tongue-in-cheek, to be honest. There are errors in there. There are plenty of them. And to be completely honest, I just haven't done all the full processing to get out. I had a brief look at some of the CP cuts, and they're not perfect, so I'm not claiming it's bad. But this is really what MeshGraphNet is kind of more designed for, predicting the pressure and the wall shear stress. We didn't do any downsampling, so it's 8 million nodes. So this took quite a long time to train. It was about 108 hours, so that's about 4 days. Still on just a few L40S, but it did increase the cost quite a bit. Most people downsample these, and so I think you could downsample it and probably get a better job. But again, the inference is still only 28 seconds, so it's still really fast. If you can get a good model, it still is incredibly cheap to do the inference. Now, what we did do, though, is we did all those models, and then we integrated to calculate the drag and the lift from the wall shear stress and the pressure. And it's actually slightly worse than the direct method, but it's not terrible. And I'm sure these models could be made better. I'm sure many of the startups have better results. But you can see now the errors, I think 8 drag counts, something like that. But again, the inference sounds pretty good. And if you look at the lift is actually probably a little bit better. So I would sort of say promising, and that's why we're encouraging other groups to take these data sets and try it. I'd love to see how some of these other codes would do. I'm sure you would do better than this, and sort of be good to get that out. So just a final thing, probably question everybody has is, well, do you need to use all the data sets? What if I just use 200, or what if I use? So this is not the most scientific experiment, I'll be completely honest, but it at least gives some sense. So this is predicting the drag with the full data set. And so that's what I showed at first. Then what if I use half the data set? Again, there should be a more systematic way of doing this, so it's not fully scientific. The error only gets slightly worse. Then I use half the data set again, and the error goes up a little bit, but it's not too bad. So the gut feeling is you probably don't need to use the entire DrivAer data set to get a decent result, but we need, a proper comparison of this. So I'm keen on transparency, and it would have been easy for me to have hide this slide and just say, there you go, it's just a driver. But I really wanted to show that it is still difficult to do these methods. And so for the Windsor, we actually, I need to dig into this. I think it's probably just a huge change in the shapes, and the data set size is just so much broader than the driver. But it seems for us harder to predict this. That you can see the traination, there's some points that are quite off. So therefore, when you do the prediction, you do have ultimately a high error. So I think it's about 13 drag counts. Similar time to train and everything else. So if you can get a good model to work, it still has the advantage. The lift is a little bit better, but this is a classic problem with ML, that overfitting when your validation sort of is higher than your training. And so to be completely honest, I think we need a lot more work on the Windsor, but this is exactly why, because we had someone say, why do you need 2 data sets? This is the reason for it. Because if you just have one, you may think your method's perfect. By having two, you can really test and see, does it work for both? And so, at least for us, the same methodology works quite well for the driver, but struggles on the Windsor. So it's good for us to revisit that. Okay, so conclusions. I think it's quite promising, and at least the work we've been doing makes me feel more positive about where this could go. That sort of thing of 90% accuracy for directional and about 1.4% error suggests to me that it could have a place in a conceptual design situation. Seems like the Windsor is a much harder data set, at least for us to do, which I didn't assume it would be at the beginning of this project. I assumed the Windsor would be easier and the driver would be harder. Obviously, I'm not showing anything on the full flow field here. I think that's a much more complicated problem to solve, but makes sense. But I tried in all the slides to always show the runtime and the cost, because at least then you can really get an understanding of the pros and cons of this. All right, sorry, I know I probably went a bit over then, but yeah, thank you.